All right, as we get started, let's go ahead and review some things we talked about in our last lesson. We've been talking about circuits. What is a circuit, Michael?
A circuit is a wire, a source, and a load that use electricity.
All right, as you've given me the parts of the circuit, which is going to be a question in a minute, but what is a circuit, Audrey? Is it pathway for current? What is a circuit?
Pathway for current.
Pathway for current. We talked about two major types of circuits based on what the electrons do in the circuit, kind of based on the source of the current as well. We talked about AC and DC. What is AC, Audrey?
Alternating current, and you plug it into the wall.
Good. AC is alternating currents for something you plug into the wall. The electrons are going to go back and forth oscillating across the circuit. Whereas DC stands for?
Direct current.
And tell me a little bit about that.
It just goes. It's from a battery and it goes.
From a battery, it goes in one direction. Good. For the parts of a DC circuit, he said it a moment ago, but we're going to echo it again, Audrey.
A battery, a conducting wire, and a load.
Good. Now the battery, and for any circuit, you need some source of the current, something to start things moving. And we said for a DC circuit, that's going to be the battery. What does the battery provide to the circuit, class?
Voltage.
It provides the voltage. It provides the push, if you will. You said conducting wires, well, that obviously provides the pathway, and also has extra electrons present. And then finally you have the load, which is, what is the load?
The load is the thing that uses the electricity.
Yep, the thing that uses the electricity, the thing that uses the current, or is powered by the current. And what is going to exist in the circuit because of the load? We said the load puts this into the circuit. Resistance. It puts resistance into the circuit. So the current is simply the flow of the electrons. The push comes from the battery, that's the voltage. And then as it uses the current, resistance is present. We talked about the wires. Do the wires have resistance in them?
Yes.
Technically, yes. Negligible amounts in a small DC circuit, but there is resistance nonetheless. Three things that affect resistance in a wire. Audrey?
The thickness, the length, the material.
Good, the thickness, length, and material. What's the equation that basically summarizes what Audrey just said, Michael?
R equals IV. No. Yeah.
Well, R equals V over I is an equation we learned, but that's not the one for resistance in a wire.
Mm-hmm.
A row, times length over A.
Good, where L is the length. A is the what, class?
Cross-sectional.
Cross-sectional area, and the rho actually stands for, what's that word? Describes a material's ability to resist the resistivity, right? You ready? Just sit forward one desk. All right, so we said that ohms is our unit, remember, for resistance. We don't usually write out the word ohms. Instead, we simply put what, Michael?
Omega.
Capital Omega. And then, of course, the resistivity, we said it's going to be ohms times centimeters. And because our book gives us ohms times centimeters, we need to make sure the length is also in centimeters, and the cross-sectional area will have to then be in centimeters squared. Ready? Take it at the side desk by the window. All right, so there's our equation for resistance in a wire. We've worked out a couple times. We'll work some more of that in our next lesson. Wanting to move on, though, we talked about something called a rheostat. What's a rheostat, Audrey? Michael?
It can change the flow of the current.
Change the flow of the current, the rate of flow, change the amount of current. Okay, that's true. How does it change the amount of current?
It uses a special coiled wire.
Oftentimes, yes. It's an adjustable resistor. Okay, it's an adjustable resistor, and as you adjust resistance, that's going to change current, isn't it? And especially if you have a set amount of voltage able to be present, whether it's 120 volts plugging into the wall, or 110 volts if you're overseas, and whether it's 9 volts from a battery or whatever, the voltage is usually set. So if you change resistance, that'll change the current and cause it to fluctuate as well. Back to Audrey for a little redemption here. Where might we see a rheostat in use? Can you give me one or two examples of a rheostat that we might use on an everyday basis? Michael?
Light switch.
Well, not so much a light switch, because that is either on or off, but a special type of light switch. The slidey kind, right? A dimmer switch.
Yes.
Right, a dimmer switch would allow for adjustable resistance and therefore adjustable current. You can think of another one where we're adjusting something? Volume control was another one I talked about in this class, where you can change, again, vary the amount of resistance. Multi-speed fan, for instance, right, would have a type of rheostat, or just different connectors, probably more in that than a rheostat, unless it was a gradual resistance. So, what's a rheostat?
It's an adjustable resistor.
Adjustable resistor, good. We talked about something called a superconductor. What's a superconductor?
It's a super cooled conductor.
Supercooled conductor, cooled down around.
Absolute zero.
And how does that work? How does it make it such a superconductor if we supercool it?
The regular electrons and nucleus and atoms aren't moving in it, so the delocalized electrons have a clear pathway.
Good. By essentially stopping or nearly stopping nuclear motion, other electron motion, allows delocalized electrons to go through without the impedance of the vibrating particles. We also talked about heat. Heat's a good thing. We can use electricity to heat our homes, heat hot water heaters, cook food, dry clothes. But how do we produce heat with electricity, Audrey?
We use high voltage and high current and resistance.
Good, just put a lot of all of it, right? High resistance should stop current, but if you have enough voltage, you can still force a lot of current through. And as you force high current through high resistance, you're going to produce heat. We had another equation besides this one. Our second equation, we actually, I introduced it before we named it. I introduced it 2 lessons ago. Last lesson we named it, called it Ohm's Law. What was that Ohm's Law equation, Michael?
V equals IR.
And this shows the relationship between voltage, current, resistance, where V, of course, is the voltage, I, we don't know why, is the current, and R is the resistance. We've already said resistance is measured in ohms. What is the voltage measured in, class?
Volts.
Volts, and current?
Amps.
Amps or amperes. We generally say amps because we're lazy. We said that for a DC circuit, we talked about the 3 parts of the DC circuit already, and said that when we draw it, the actual circuit is really just, kind of more or less a box, if you will. However, at some point in the circuit, we'll put in the source of the current, the voltage producer, that which pushes things along, the battery. How do we say we'll see a battery visualized in a schematic?
Lines.
2 lines, and one is?
Shorter.
One's shorter, one's longer. So we'll have a short little line and we'll have a longer line. Now, technically, the short line represents the negative terminal and the longer line represents the positive terminal. In which direction do we suppose the current to flow?
Positive to negative.
From positive around to the negative. Now, in reality, that's counterintuitive. If the flow is the flow of electrons, it should go the other way. We call this, though, this assumption of positive to negative. We call this, just because we've always done it ever since Ben Franklin, conventional current. Now, along the way, obviously, if the current just flows from a battery and then back into the battery, no good is being done. We need to have the loads, something to use the current. I said we could draw the loads a couple different ways. Audrey, do you remember how we draw the loads?
Zigzag.
Ziggy-zag lines, squiggly lines, so to speak, though more of a true zigzag if it's drawn properly. I'm usually kind of fast with my drawings. And somewhere along the line, it'll start to zigzag for a little bit before returning back to normal. Now, technically, we said a load should have a circle around it, but I said I'm too lazy. The load ultimately provides resistance. That's the aspect of the load we'll care about, because in a schematic, I can't tell how bright that light bulb is. I can't feel the cooling effects of the fan. I can't benefit in any way. It's just a schematic. So I'm going to be lazy and not draw the circle, because I'm really just focused on the resistance that's there. And we could have, of course, lots of ziggy-zag lines, right? Lots of resistances. And but if they're all in a line, if the current goes through one resistance, then the next, before finally getting back to the battery, then this is what type of simple DC circuit, Michael? If you're a sports guy, you think about two teams, they play each other over and over and over again, one day after the next, until the winner's been determined. Does that help?
Series.
Series, there we go, a series. So we call this a series circuit where this current passes through one connector at it, or one resistance, one load at a time. Can't go through them all at once. Now, it looks like it's all at once, right? Because there's already electrons here. As soon as you push these electrons, that pushes these, which pushes those. So they all get pushed at the same time. But the current itself, the flow of electrons, slowly, that drift velocity we talked about, works its way around the circuit back to the battery. And the current will actually flow through one, then eventually the electrons get there, then eventually there and back to the battery. For a series circuit then, if we have different resistance amounts at each of the loads or each of the resistors, we'll want to determine how much resistance there is total, how much in all, so to speak. And we call the total resistance of a circuit the big fancy name. Start with an E. Michael?
Equilibrium.
Not equilibrium, but it's close. Equivalent resistance. What is it, class?
Equivalent.
Equivalent resistance. We'll notate that R sub EQ for equivalent resistance. Audrey, do you remember how I said in a series circuit, and we didn't get to do a lot of these. I think I showed one example and we ran out of time because of camera problems. Anyway, but how would I find the equivalent resistance of some series circuit?
You add all of them.
I just add all the resistances. In this case, there's 3 resistors or 3 loads, so I simply add the 3 resistances. If there were more, I would add more. You literally just add them up. Really easy math you can do in your head, most cases. Questions on what we talked about through last time? All right, let's pick it up there then, page 387 in your textbooks. And what we did not get a chance to do in the last lesson was look at the example problem 25.3. Example 25.3. Go and read the example problem for us if you would, Michael.
A DC circuit is connected to a battery of 12 volts. External to the battery is a series of 4 pure resistances, 15 ohms, 15 ohms, 10 ohms, and 25 ohms. What is the equivalent resistance? What is the current in each resistance? What is the IR drop across each resistance?
All right, so we got a lot going on here. First thing we want to do is draw some kind of circuit. So if you have some space in your notes, let's go ahead and draw this. I always like to start by drawing the battery first. So I'll draw my 2 parallel differing length lines. And there's 4 resistances. Now, you can get creative. I had 3 resistances and I put 1 on each side of the rectangle. Does it really matter? No. If I wanted to, I could have 1 right away out of the battery, and I could go up and I could go a long time before I have any more. I could put the other 3 all in a line before returning to the battery. As long as it goes through one, then the next, then the next, then the next. Really doesn't matter. Okay, the advantage of something like this, you spread them out a little bit better, but it really doesn't matter the order in which you place them, or the way in which you arrange them on their circuit. We should label the battery on the schematic. It tells us in the problem, Michael, that the battery provides
12 volts.
12 volts. And I'm also going to label on the schematic the resistance at each resistor or at each load. Audrey, the first resistor they mentioned has a resistance of
15 ohms.
the next one, 15 ohms again, then 10 point ohms, and then
25.
wow, 25 ohms. So that's a lot of resistance there. For any circuit that we work in this class, we're always going to start by finding the equivalent resistance. That's always your first step to any circuit. How much resistance is in this? And for this, it's really straightforward. You just add them up. And what do we get when we add all the resistances together, class? 65 ohms. Again, oftentimes, even with weird numbers like this, it's not hard to add that in our heads. Quiz or test might be good to plug it in the calculator just to be on the safe side, or do you check yourself with the calculator because you hate to get that wrong. If you blow the first number, you're doomed to blow the rest of the problem, okay? So, got to get the first number. That's the first thing it asked for, by the way. That was letter A. The second thing it asked for was the current across each resistor. Remember what I said in the last lesson. When the current is pushed by the battery, there is only one path. It has to go here, 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 and back. So whatever current the battery is able to provide, all of that current goes across every single resistance. The second thing we'll always find is what I call the total current in the circuit. Sometimes you'll see it notated this way, I sub battery, meaning the current the battery is able to provide. I usually label it I sub total, meaning total current. So we find total resistance or equivalent resistance, then we find total current. How do you suppose we'd find total current? Well, go back to Ohm's law, V equals IR, right? If I know the total voltage, 12 volts of electrical potential difference, if I know the total resistance, 65 ohms, then I should be able to find the total current by getting I by itself. I is going to equal, class, V over R. Total, we have 12 volts. Total, we have 65 ohms. So total on your calculators, we don't have much current at all. How much current do we get?
0.184.
About 0.18.
1.
Right, well, yeah, sorry, I was rounding to 2 sig figs. 0.18
Amps.
amps, there we go. Put this in the memory of your calculator, because it doesn't work out evenly. It's a weird number. I don't even see a repetend in here, so let's store that so we can use it later. Once we've established the total, the big picture, 12 volts from the battery. Now remember, the analogy of the car going through the different loops in the racetrack. It loses a little of that electrical potential difference. Loses a little more, loses a little more, loses a little more. We call this the voltage drop or the IR drop. It's going to lose a little in each resistance. Total, though, there's 12 volts. Total, there's 65 ohms. Now we're going to go down to a smaller scale. We're going to set up a chart. I want you to set this chart up with me, if you would, please. For the first column, put R. This is the resistor. And we're going to list out the individual resistances. My first resistance has 15 ohms. Second resistance, 15 ohms. Next resistance, 10 ohms. Final resistance, 25 ohms. This way your answers and your work stay neatly organized. The second column is almost insulting to fill in for now, but we're going somewhere with this, so bear with me. The second thing we're going to list out is the current, or the I, that goes through each resistor. Now again, it's the same current. It's the 0.18 amps everywhere. So for every one of these, it's 0.18 amps. Like I said, we're going somewhere with this. So it seems tedious for now, but bear with me. 0.18 amps will list our current that goes through each resistance. The final column is to find, by the way, that answers question B. What is the current in each resistance? Bam, 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 bam. 0.18 amps for all of them. The third thing it asks for is what is the IR drop, the voltage drop across each resistance? How much of that push is used up? How much of that push is lost? How much decrease in electrical potential difference is there as the voltage pushes current across each resistance? Well, here's the deal. IR drop. Here's I, here's R. They want IR. What do you suppose we should do? What's in the memory of the calculator times 15? 2.76. Ooh, so let's round to 2.8. Let's say 2.8 volts. And we don't need to plug it into the calculator again. What's the next one going to be? Another 2.8 volts. Or what about the next? We can do this without a calculator. 1.8 volts. And then the 25 ohms.
4.615.
4.61, so 4.6 volts. Now, there's a way we could check our work. We could add these together and see if it comes to about 12 volts. 2.8 plus 2.8 plus 1.8 plus 4.6. Does that add up to 12? It does. Now, occasionally, because of rounding, it may add up to either 11.1 or 12.1. You might be 1/10 of a volt off, but that's a good way to check your work. And this answers all the questions. This is called analyzing a circuit, where you find the equivalent resistance, find the current, and then at every individual load, how much current's going across it, how much voltage is getting used. What is the IR drop? Any questions on this? See the basic strategy. All right, let's do another one here. This time, let's take a 9-volt battery. Your typical 9-volt battery. And let's suppose the current goes across a 3 ohm resistor. Then it goes across a 6 ohm resistor. Goes across a 4 ohm resistor. And finally, on the way back to the battery, it hits one last resistance of 2 ohms. First thing we'll find for any circuit class, total resistance, equivalent resistance, REQ. And for a series circuit, you just add them up. And what do we get? 15 ohms. Now, if we were going strict sig figs here, we'd have to round to 20 because we only have one sig fig everywhere. Imagine, use your imagination here because I'm lazy, right? Imagine I said 9.0, 3.0, 6.0, 4.0, and 2.0. Okay, so we're going to say 2 sig figs for this problem. On quizzes or tests, I'll make sure I put the sig figs I want. But for a problem in class, I'm just too lazy to keep writing the point zeros. Once I know the equivalent resistance, I want to find how much total current there is. All right, so I've got the equivalent resistance. I now want the total current, the current flow through the circuit. To figure this out, I need Ohm's law, but I'm solving it for the I. What does it look like? I equals V over R. The total current equals the total voltage, or the voltage of the battery, divided by the equivalent resistance in the circuit. As we just divide, and what do we get? But since I said 2 sig figs, we'll say 0.60 amps. Those are your first 2 big numbers. Once we've got those, we need to fill in the chart. So enlist your resistances. 3 ohms, 6 ohms, 4 ohms, 2 ohms. Next one. Help me. Did you already have it? Was it coming?
Yeah, I already had it.
Yeah, right. That's right. You skipped out on school day. You did it. You did, yeah. So we didn't sing happy birthday. Yes, we did. Just because we love you. That's what it is. Something like that.
Pastor Adam was supposed to get them to take me off the list. I forgot.
All right, we want to fill in the current through each resistor, but what do we remember about a series circuit? There's only one current. There's only one path. So whatever the current is, that's what it is, right? So for every single one of these, did you already fill out your current? For every one of them, class, it's just 0.60 amps over and over and over again. However, although the current is constant, the voltage is going to vary. The more the resistance, the more voltage gets used, right? If you have a little turn, that doesn't use a whole lot, but if you have a loop, the bigger the loop, right, in the racetrack, the more speed might be lost on that initial going up. Now, supposedly regain it coming back down if you ignore friction. But yeah, so we're looking at the IR drop here, multiplying by each. So 3 ohms, 8.6 amps uses up how much voltage? 1.8 volts. What about 6 ohms?
3.6
4 ohms,
2.4.
and finally 2 ohms.
1.2.
And if we add them up, we could check and make sure it adds up to 9 volts, and it does. All right, so let's summarize the series circuit here in your notes. Series circuit summary. series circuit summary. I like that alliteration. Number one, current through each load is constant. Current through each load is constant. There's that alliteration again. Current through each load is constant. Number two, IR drop or voltage, IR drop or voltage varies at each load. IR drop or voltage varies at each load. Current is constant, voltage varies. Number three, I subtotal, current, total current, I subtotal equals V sub battery, voltage of the battery, over R sub EQ, equivalent resistance. I subtotal equals V sub battery divided by R sub EQ. Lots of fun subnotation. Total current equals the voltage of the battery divided by the equivalent resistance. And, along that note then, equivalent resistance, R sub EQ, equals R sub 1 plus R sub 2 plus R sub 3, etc. This is for a series circuit. This would be like old style Christmas lights. String of lights, current goes through the wire, into a light bulb, through the light bulb to the next light bulb, over and over and over again. One bulb blows, everything's done, everything's toast. Nowadays, they reconfigure Christmas lights, right, to where they do have sets of series, but they're all strung together where the current could bypass one strand and go to another strand instead, right? So there's multiple pathways for the current to follow. Not everything is just series circuit, because again, one load blows, it's all done. Multiple pathways is often better, but the series doesn't have that. Let's talk then about a multiple pathway circuit. It's called a parallel circuit. A parallel circuit. If you looked at Adam's display at the academic fair the other day, you might have noted that he had little clumps of Christmas lights arranged in different sizes of clumps, different numbers of clumps, always adding up to 12 Christmas lights total, and the lights were of different brightnesses. You also noticed that there was nothing parallel about the Christmas lights. They were just all over the place. It was a jumbled mess. Kind of had okay, this is where the nut is, how many wires are coming out of the nut, and that kind of thing to figure out what we had going on there. It's called parallel because when we draw a schematic and everything is drawn with straight lines, it's going to look parallel on the schematic. But we understand that in practice, the pathways are not necessarily running neatly side by side. Does that make sense? That said, here's your definition for a parallel circuit. The current goes through all resistances or loads at once. The current goes through all resistances or all loads at once. Current goes through all resistances at once. Not going through one, then the next, then the next. Put this in parentheses. This is because we have multiple pathways. We have multiple pathways. Current goes through all resistances at once because we have multiple pathways. Well, if we have multiple pathways, what do you imagine those delocalized electrons are going to do when they come to a spot where they could go a lot of different directions? Do you think they'll all channel down one way? Not if there's multiple directions, right? They'll pick multiple paths. Some will go down each of the different paths. So because there's multiple pathways, we understand then that current splits and varies, understandably, by resistance. Current splits and varies by resistance. Current splits and varies by resistance. I mentioned the junior high hallway at my school. No place to be avoided unless you were in junior high and couldn't. And then you didn't even notice because, well, you were the reason. It was the anyway. So we had the junior high hallway. You didn't want to take that route if you didn't have to. There was also, we could cut through the library, but imagine if there was a group of elementary classes assembled just inside the library door. And then there was a stairwell that took you down around the cafeteria, so it was a little bit of a longer way, but that could work. And there was a way further back down that you could take. There were a lot of different ways to get from one side of the school to the other. And so there were multiple pathways. Understandably, I would want to take the quickest way. If there was a block, I'd take a different way. You come from Phoenix City into Columbus every day. You live in Columbus and Kendall lives way out wherever. So you can relate. You're my one person who can relate here. When there's a wreck on J.R. Allen Parkway, everybody starts to channel through downtown, which I think is the way you come normally. Is that right? Or do y'all go up J.R. Allen? I was going to say, you probably go through downtown because you live down on that end of Phoenix City. So you notice the traffic is busier certain days. And it's like, oh, I bet there's a wreck up on the freeway. Yep. And so when people are choosing the path of least resistance. Unfortunately for us, there's only really 3 good ways to get across the river, right? Well, 4. There's 4. There's the one way downtown by the Civic Center. There's the way you come. There's Dillingham Street for those who want to go that way. And then there's the freeway that most of us take. The electrons are going to take the path of least resistance. So if we've got multiple pathways, we could get from this point to this point, and there's a pathway that has, say, 5 ohms of resistance, and there's another pathway, for instance, from this point to this point, that has, for instance, 10 ohms of resistance, and there's another pathway, for instance, that has, let's just say, 20 ohms of resistance. First, second, or third pathway, where is most of the current going to go?
First.
It's going to go through the first pathway. There's less resistance there. Half as much current will go here. 1/4 as much current would go here. It varies by resistance. The more resistance there is in a pathway, the less current is going to go through. But when the current gets to this point, you realize all the current has the exact same push coming up on it, right? So as the current splits and goes down the various pathways, it all has the exact same push behind it. If there are no more resistances after these 3, all the voltage gets used at once. And all the voltage is exactly the same as it hits that set. So the voltage is constant. Same voltage across every one of these because no voltage has dropped yet. There hasn't been a decrease in electrical potential difference. No voltage drop, no IR drop has happened. So whatever the voltage is the battery puts out, that's what you've got right there. And it all uses up at once. But because the voltage is constant, that's also why the current has to vary with resistance. Does that make sense? Interesting as well, what if we were to find equivalent resistance? Well, let's just suppose for a moment that these pathways didn't exist. How much resistance is there? Help me out here. 5 ohms. I know you're tired. 5 ohms of resistance. If I add another pathway, and it has 10 ohms of resistance, I may be adding another resistance, but I'm also adding another path. Even if more of the electrons choose to go this route, that's still some of them that don't have to go this way anymore. They are no longer resisting each other in any way, right? Like even if all the cars are going this way, cars can still get in each other's way even if we're all flowing the same direction. So by adding an alternative route, that actually will decrease resistance. Resistance drops from 5 down to something like, if I try to do it in my head, I probably shouldn't, so let's not, but it might drop to say 4 or 3 ohms of resistance. By adding a bigger resistance, it still drops. Even when I add the 20 ohm resistance in here, well, all I did was take electrons that would have had to go this way, and some of them, not many granted, take this pathway. I've literally decreased resistance by adding, don't think of it as another resistor, though I did, think of it as I added another pathway. The more pathways you have to choose from, the less the overall resistance. This is why at fire drill, we try to come up with, okay, these classes go this way, these classes this way, these classes this way, you use this hallway. We try to map it out so we have as many, an equal amount using all pathways so there's no bottlenecks. Kind of the same idea here. So does it make sense then that the equivalent resistance of a parallel circuit will be less than any individual resistor? The equivalent resistance of a parallel circuit will actually be less than any individual resistor. The more you add, when he gets back, the more you add, the less resistance there is in a parallel circuit. Do we kind of understand the thought behind this? Mathematically, how does this work then? Here's your next formula. If we were to take reciprocals, every time you add a reciprocal value, you're diminishing overall value, correct? Because you're adding a fractional portion. So the reciprocal of equivalent resistance equals the reciprocals added together. Very similar equation. We just need to remember that for the parallel circuit, we use the reciprocals of everything. 1 over R sub EQ equals 1 over R sub 1 plus 1 over R sub 2 plus 1 over R sub 3 and so on and so forth. Isabella, here we go. Questions on this? All right, so let's look very quickly at an actual parallel circuit. I say actual, okay, one drawing board. We have parallel circuits at the academic fair we can look at. Let's suppose we go back to that 6-volt battery that we had in our first illustration of a basic circuit. But instead of going to a single 6 ohm resistance, which gave us 1 amp, let's suppose we had 4 ohms here, and we add another pathway with 2 ohms here. So we still technically have 6 ohms worth of resistors, but by putting them in parallel, we don't have 6 ohms of resistance. Let's see, first of all, what is the resistance going to be? Again, the reciprocal key on your calculator makes it work. You'll start by taking the reciprocal of 4 plus the reciprocal of 2, and then take the reciprocal of that. And what do we get for the equivalent resistance, Audrey?
1.3 repeating.
1.3 repeating, we'll round off and say 1.3 ohms. Now, you ask yourself, does that make sense? Yes. We know the equivalent resistance has to be smaller than the smallest resistor. The smallest resistor is 2. If this were the only resistance, we'd have 2 ohms. We added another pathway. That allows a flow of electrons to find another route to take. Even though half as many will take this route, it still diminished the overall resistance. We now are down to only 1.3 ohms of equivalent resistance. Michael, did you get that?
I keep getting 0.75.
Okay, remember, it's 1 over REQ, so don't forget the reciprocal at the end. Kind of like with the 1 over F, where you have to take the reciprocal at the end, right? So same kind of thing here. So if you need to put a star next to that or write yourself a note and highlight it, don't forget the reciprocal at the end. Do what you need to on that. Now think about this. Think about this. Total resistance, 1.3 ohms. How much current then is able to go through? Well, we have 6 volts and 1.3 ohms. Let's do what we just did a moment ago with a series circuit. Divide the voltage by the resistance. 6 divided by the 1.3. How many amps of current flow through this circuit? 4.5 amps. Notice last time when we're dealing with the series circuit, as we kept putting more and more resistances in, increasing the resistance more and more, we got less and less current. Here we add more and more resistances, we get less and less equivalent resistance. More and more current able to flow through. Well, understand this though. Some of that 4.5 amps goes here. Some of the 4.5 amps goes here. Right? Total there's 4.5 amps. But what is constant is all the current gets pushed by the same 6 volts. 6 volts pushes at the same time across both of them because none of the voltage has been lost yet. It hits them at the same time. So as we set up our chart, it'll be a little bit of a shorter chart this time with our 4 ohms and 2 ohms. This time we don't already know the current through. 4.5 amps doesn't go through both of them. The 4.5 amps splits. But we do know that the IR drop at both of them is the same 6 volts. Do you see that? So, how would I find the amount of current that goes through just the 4 ohm resistor? Well, just like we just said I equals V over R, we can say I equals V over R. There's V, there's R, V over R becomes 1.5 of the amps goes through the 4 ohm resistor. How much of it goes through the 2 ohm resistor? 3.0 amps. Notice that's the 4.5 amps. Twice as much through the smaller resistance. This is twice as much resistance, half as much current, 1.5 amps. Do you see that reciprocal relationship? Twice as much of this, half as much as that. Does that make sense? Also, does that make sense why we use reciprocals for this? All right, so remember I said for a series circuit, current is constant and voltage varies. It's all really nicely alliterated. For the parallel circuit, nothing's alliterated. Parallel circuit, current varies and voltage is constant. Everything's mixed up. There's no alliteration. So if that pneumatic or mnemonic device helps you, remember series circuit, everything's alliterated. Parallel circuit isn't alliterated, so nothing's alliterated, if that helps in any way. All right, or I guess it's not technically alliteration. It's not the same. Is alliteration sound or letters? Alliteration. I think that's the starting letters. It's consonants. That would be the starting consonant sounds, right? I don't know. I'm not an English teacher. At least not literature. All right, grammar I'm not too bad with, but literature. Anyway, writing poetry and whatnot. All right, questions on this? Let's do one more example then for your notes. Page 389. So flip over just another page from where you were at. You see something fun at the bottom of page 389. It's okay, not till after senior trip. Okay, we're not going to do that till after senior trip. Let's look at the top of page 389 and cause your heart rate to go back down. Example 25.4. Audrey's like, I'm not coming back from senior trip. Kendall, make her come back from senior trip, okay? Help me here. Bring her back in one piece. All right, example 25.4. Read it for us, Michael.
The resistances of 20 ohms, 30 ohms, and 40 ohms are joined in parallel. If the battery is 18 volts, what is the equivalent resistance? What is the current outside the branches? What is the IR drop across each branch? And what is the current in each branch? Assume that there is no resistance apart from what is stated.
When it talks about a branch, that's this right here. The branch is the thing that has the resistance in it. So this is a branch, and this is a branch. Does that make sense? Okay. And that's a term that I will be using a little bit more when we get into the complex circuits later. For now, we need to go ahead and draw a picture. So draw a battery, and label it as an 18-volt battery. Have the current come up and go across a resistor and back to the battery. The first resistance is a 20 ohm resistance. But we have another resistor, a 30 ohm resistor. So at this point, allow the current to take a, now reality. If these are actual wires, they just kind of curve like this, okay? But in a schematic, we use right angles for everything. So we're going to draw up, over, squiggle, over, down. But we understand that the split is happening at this point, correct? That whole thing's a branch. And then we could add another branch. It could also come up here, go over, and down. Does that make sense? So there's our 30 ohm resistance, and then finally our 40 ohm resistance. Big resistances. A lot of ohmage. Not homage, that's what the scum of earth pays to the grand high royal exalted seniors. Oh, they don't. Okay. They should, right? They should. Homage is what they... All right. Anyway, first thing we need to find is the equivalent resistance. R sub EQ. And for this, remember reciprocals. Reciprocal of 20 plus reciprocal of 30 plus reciprocal of 40, and then take the reciprocal again. Well, what do we get for the equivalent resistance? And I think they actually have 3 sig figs in the problem. So yes, we'll say 9.230, 9.23 ohms of equivalent resistance. Again, we knew it had to be less than 20, right? Because by itself, we would have had 20 ohms. Adding pathways just makes the number get smaller and smaller. Second thing we need to find is the total current. How do I find total current? V over R, the voltage of the battery divided by all the resistance we got. If you use the memory value, this will come out to a nice, easy number. If you round it to 9.23, it'll be really close to a nice, easy number. 3 sig figs. I get exactly 1.95 amps. So if you put the 9.230 blah 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 in the memory, it would come to exactly 1.95. As is, you probably got something that rounded there, right? 1.94 or 1.95, something like that. All right, stay with me real quick. Let's finish out the problem. 8th graders, you're dismissed. Please leave quietly. Let's set up our chart very quickly. Let's finish this out. We've got 20 ohms. We've got 30 ohms. We've got 40 ohms. The first thing we'll find for every one of these is how much current goes through. But we don't know that. Remember, current varies. But one thing we do know is constant in a parallel circuit. What is constant, class? Voltage is constant in a parallel circuit. The IR drop. They all drop the voltage at once. They all have how many volts? 18 volts. 18.0 volts technically for going 3 sig figs. And how do I find I? V over R. So we'll take the 18 divided by the 20. We get 0.900 amps. 18 divided by the 30. 0.600 amps. And 18 divided by the 40. 0.450 amps. Altogether, there's your 1.95 amps of current. Despite the big resistances we had, by putting them in parallel, we were still able to get pretty decent current flow. Questions on this? Homework for this evening is to do page 398. Page 398, problems 5 through 7. Page 398, problems 5 through 7. All right, we'll take a look at those in our next lesson. Have a wonderful rest of your day, and you are dismissed.